Polynomial inequalities are solved just like quadratic inequalities, except that there are usually more boundary points, which means more intervals to check. Remember, the boundary points are also called zeros, the values that make the corresponding equation equal to zero. The first example is already in standard form. It is also already factored for us. We just need to solve the corresponding equation to get the boundary points. Place these values on a number line. Since this is a less than problem, I will use open circles. I now need to choose some test points within each interval. I will test each value to see if I get a true statement. Since 2 yields a false statement, then the numbers that are larger than 1 will not satisfy the inequality. Zero gives us a true statement, so all the numbers between -4 and 1 will be part of the solution. -5 gives us a false statement, so that interval is not part of the solution. -10 yields a true statement, so all the numbers less than -7 will be part of the solution. We need to write our answer in interval notation. Let us now look at the graph of the corresponding function. We still have the same zeros. Notice that is where the graph crosses the x-axis. Since the inequality asks us to find values less than 0, we need the part of the graph below the x-axis. This gives us the same answer that we found by testing the intervals. This problem is just like the previous one. It is in standard form and already factored. We just need to solve the corresponding equation. Place the values on a number line and choose a number in each interval. This time I have to choose decimals or fractions. I start the testing procedure. Since 0 yields a true statement, I will shade that part of the number line. You could use a calculator or just look at the signs when you're testing -1.5. Since I have one negative multiplied by 2 positives, I know my answer will be negative. A negative number is never greater than 0. Once again, the decimals are messy. Since I don't have a calculator nearby, I will just look at the signs. I have 2 positives multiplied, and that equals a positive. Positive numbers are always greater than 0. I will shade in that interval on the number line. I will now test my last number. Since this is a true statement, I will once again shade in that part of the number line. I am ready to write my answer in interval notation. Let us now look at the graph of the corresponding function. We still have the same zeros. Notice that is where the graph crosses the x-axis. Since the inequality asks us to find values greater than 0, we need the part of the graph above the x-axis. This gives us the same answer that we found by testing the intervals. This problem is not in standard form. We need to subtract 30x squared from both sides and write the left-hand side in descending order. This time we need to factor out the GCF of 2x and then factor the remaining trinomial. We now have our zeros, and we will place them on the number line. It might be helpful to know the decimal approximations for these fractions so you can choose appropriate test points. I start the testing procedure, but this time I have a choice as to what form of the problem to use. I can use whichever one I want or the one I think would be easiest to do the arithmetic. I am going to use the factored form because I think the arithmetic is easier. Shade the intervals that yield a true statement. I once again don't have a calculator, so I know that 0.3 minus 4 is negative and 0.3 minus 1 is also negative. Since two negatives multiplied makes a positive, then I know I have a positive answer, which is always greater than 0. I have three negatives multiplied together here, which makes negative. A negative is never greater than 0. Shade the intervals and write your answer in interval notation. Let us again look at the graph of the corresponding function. We still have the same zeros. Again, notice that's where the graph crosses the x-axis. Since the inequality asks us to find values greater than 0, we need the part of the graph above the x-axis. This gives us the same answer that we found by testing the intervals. Here we need to write this problem in standard form. Subtract x and subtract 4 from both sides. Since we have 4 terms, we will use the grouping method to factor and solve for x. We can factor further because we have the difference of two squares. We now have our boundary points, our zeros. Place on the number line and choose your test points. Follow the same procedure as before. Again, you can choose what form you want to substitute your test value into. This time I'm using the unfactored form because the arithmetic is so much easier. Once again, I'm just using the signs here, but you could also do the arithmetic if you want to. Shade and write your answer. Again, look at the graph of the corresponding function. We still have the same zeros. Remember, the zeros are the x-intercepts. Since the inequality asks us to find values less than 0, we need the part of the graph below the x-axis. This gives us the same answer that we had before. This problem is like the previous one. We need to use the grouping method to factor and solve. We cannot factor further. We have the sum of two squares. Just set equal to 0 and solve. We have the square root of a negative number, which is imaginary. We cannot place imaginary numbers on a real number line, so we have only one boundary point. We choose a number on either side of -5 and test these two intervals. Notice that I have used a closed circle because of the greater than or equal sign. Shade and write your answer. Look at the graph. It only crosses the x-axis one time at -5. The part of the graph above the x-axis has a domain of -5 to infinity. This once again verifies our answer from testing the intervals.